Welcome to Database Internals Crashcasts. I'm your host, Sheila, and today we're diving into the fascinating world of query processing and execution. Joining me is our database expert, Victor. Victor, are you ready to unravel this complex topic for our listeners?
Absolutely, Sheila. I'm excited to share my knowledge about query processing and execution. It's a crucial aspect of database management that often goes unnoticed, but plays a significant role in system performance.
Great! Let's break down today's episode into sections. We'll start with a brief history, then move on to basic concepts, gradually increase complexity, discuss real-world implementations, and finish with best practices and tips. But before we dive in, I have a quiz question for our listeners. Victor, what do you think about this one? In query optimization, what does the term cardinality refer to?
Ooh, that's an excellent question, Sheila. It's definitely something that plays a crucial role in query optimization. I'm curious to see how many of our listeners are familiar with this term. Let's keep them guessing for now and reveal the answer later in the show.
All right, let's start with the history. Victor, can you tell us about the origins of query processing and how it has evolved over time?
Certainly. Query processing has its roots in the early days of relational databases, dating back to the 1970s. Initially, query processing was quite basic, with simple table scans and nested loop joins. As databases grew in size and complexity, the need for more efficient query processing became apparent. This led to the development of various optimization techniques and algorithms throughout the 1980s and 1990s. Today, we have highly sophisticated query processors that can handle complex queries across distributed systems and massive datasets.
That's fascinating. So, let's break down the basics. What are the main steps involved in query processing and execution?
Great question. Query processing typically involves three main steps: parsing, optimization, and execution. First, the SQL query is parsed to create a logical plan. Then, the query optimizer generates multiple possible execution plans and selects the most efficient one. Finally, the chosen plan is executed to retrieve the results.
I see. So, if I understand correctly, when I write a SQL query, the database doesn't just immediately execute it as is, but goes through these steps to figure out the best way to get the results. Is that right?
Exactly, Sheila. That's a great way to put it. The database management system, DBMS, tries to be smart about how it executes queries to ensure optimal performance.
Now let's dive a bit deeper into query optimization. What are some of the techniques used to optimize queries?
Query optimization is a complex topic, but I'll try to break it down. There are two main approaches: rule-based optimization and cost-based optimization. Rule-based optimization applies predefined rules to transform the query into a more efficient form. Cost-based optimization, on the other hand, estimates the cost of different execution plans and chooses the one with the lowest cost. This cost is typically measured in terms of CPU usage, I/O operations, and memory consumption.
That's interesting. Can you give an example of a rule that might be applied in rule-based optimization?
Sure, a common rule is pushing down predicates. For example, if you have a query that joins two tables and then applies a filter, the optimizer might push the filter down so it's applied before the join. This can significantly reduce the amount of data that needs to be processed in the join operation.
I see. And what about parallel query execution? How does that fit into all of this?
Parallel query execution is a technique used to improve performance by dividing a query into smaller parts that can be executed simultaneously on multiple CPUs, or even across multiple machines in a distributed system. This is particularly useful for large, complex queries on big datasets. The query optimizer needs to consider how to split the query and how to combine the results efficiently.
That sounds complex. What are some of the challenges in implementing parallel query execution?
Good question. One of the main challenges is ensuring that the overhead of parallelization doesn't outweigh its benefits. There's also the challenge of data skew, where some parallel tasks might take much longer than others, reducing the overall benefit of parallelization. Additionally, managing distributed transactions and ensuring data consistency across multiple nodes can be tricky.
I can see how that would be challenging. Are there any particular edge cases or situations where query processing becomes especially difficult?
Absolutely. Complex joins, especially those involving multiple tables, can be challenging to optimize. Subqueries, particularly correlated subqueries, can also be tricky. Another challenging scenario is dealing with very large datasets where not all data can fit in memory. In these cases, the query processor needs to be smart about how it accesses and processes data to minimize I/O operations.
That makes sense. Can you tell us about some real-world implementations of query processing systems? How do different database management systems approach this?
Certainly. Let's look at three popular DBMSs: PostgreSQL, MySQL, and Oracle. PostgreSQL uses a cost-based optimizer and is known for its advanced query planning capabilities. It can handle complex queries well and has good support for parallel query execution. MySQL traditionally used a simpler rule-based optimizer, but in recent versions, it has introduced a cost-based optimizer called the Query Optimizer Framework. Oracle, being a commercial product, has one of the most advanced query optimizers in the industry, with sophisticated cost estimation and plan selection algorithms.
That's really interesting to see how different systems approach the same problem. How does query processing in traditional relational databases compare to newer technologies like NoSQL databases or stream processing systems?
That's a great question. NoSQL databases often have simpler query models compared to relational databases, which can make query processing less complex in some ways. However, they face their own challenges, particularly when it comes to distributed query processing across multiple nodes. Stream processing systems, on the other hand, deal with continuous queries over unbounded data streams, which requires a different approach to query processing. Instead of processing a fixed dataset, they need to continuously process incoming data and update results in real time.
I see. Now let's talk about some common misunderstandings or pitfalls in query processing. What should developers be aware of?
One common misunderstanding is that adding more indexes always improves performance. While indexes can speed up data retrieval, they also slow down write operations and take up storage space. Another pitfall is writing overly complex queries when simpler alternatives exist. Sometimes, breaking a complex query into multiple simpler queries can lead to better performance. Also, developers should be aware that query plan caching, while generally beneficial, can sometimes lead to suboptimal plans being reused when data distributions change.
Those are great points, Victor. Do you have any best practices or tips for writing queries that are easier for the query processor to optimize?
Absolutely. First, try to write queries that filter data as early as possible to reduce the amount of data processed. Use appropriate indexes, but don't over-index. Be cautious with subqueries, especially correlated subqueries, as they can be performance bottlenecks. When dealing with large datasets, consider using partitioning to improve query performance. And always test your queries with realistic data volumes to ensure they perform well in production scenarios.
Those are excellent tips, Victor. Before we wrap up, do you have any interesting facts about query processing that our listeners might find surprising?
Here's an interesting one. Did you know that in some cases, a query optimizer might choose to ignore an index even if it exists? This can happen if the optimizer estimates that a full table scan would be faster, which can occur if a large percentage of the table needs to be read anyway.
Wow, that is surprising. Now let's reveal the answer to our quiz question. Victor, can you explain what cardinality refers to in query optimization?
Certainly. In query optimization, cardinality refers to the number of unique values in a column or a set of columns. It's a crucial concept because it helps the query optimizer estimate how selective a predicate will be. For example, if a column has low cardinality, few unique values, a filter on that column might not reduce the result set much, which affects how the optimizer plans the query.
Thank you, Victor. That's a great explanation. To summarize today's episode, we've covered the history and evolution of query processing, the basic steps involved, Optimization techniques including cost-based and rule-based optimization. Parallel query execution. Challenges with complex queries and large datasets. Real-world implementations in different DBMSs. Comparisons with NoSQL and stream processing. Common pitfalls and best practices.
That's a great summary, Sheila. If we had more time, we could have delved deeper into topics like adaptive query processing, approximate query processing for big data scenarios, or the impact of hardware advancements like SSDs and in-memory databases on query processing strategies.
Those sound like fascinating topics for future episodes, Victor. Thank you so much for sharing your expertise with us today. To our listeners, if you enjoyed this episode, please subscribe to Database Internals Crashcasts and leave us a rating. Your support helps us continue to bring you in-depth discussions on database internals. Until next time, happy querying.